Welcome to Orchestrate All the Things. I'm George Anatiotis and we'll be connecting the dots together. Stories about technology, data, AI, and media and how they flow into each other, shaping our lives. Organizations are facing a critical challenge to AI adoption: how to leverage their domain-specific knowledge to use AI in a way that delivers trustworthy results. Knowledge graphs provide the missing truth layer that transforms probabilistic AI outputs into real-world business acceleration. Knowledge graphs are powering products for the likes of Amazon and Samsung. The knowledge graph market is expected to grow to $6.93 billion by 2030 at a compound annual growth rate of 36.6%. Gartner has been advocating for the role of knowledge graphs in AI and the downstream effects in organizations going forward for the last few years. Neither the technology nor the vision are new. Knowledge graph technology has been around for decades, and people like Tony Seale were early to identify its potential for AI. Seale, also known as the knowledge graph guy, is the founder of the eponymous consulting firm. In this extensive conversation, we cover everything from knowledge graph first principles to application patterns for safe, verifiable AI, real-world experience, trends, predictions, and the way forward. I hope you will enjoy this. If you like my work on Orchestrate All the Things, you can subscribe to my podcast, available on all major platforms, my self-published newsletter, also syndicated on Substack, HackerNoon, Medium, and DZone, or follow Orchestrate All the Things on your social media of choice.
Yeah, hi. Thanks for having me on the podcast. That's really nice to be here. I'm Tony Seale, also known as the Knowledge Graph Guy.
Well, yes, it's true that between you and me, we do know what a knowledge graph is, I hope. However, that's not necessarily the case for everyone else who may be listening. So whenever I'm having this conversation and in the presence of an audience that I know is not necessarily familiar with the term, the first thing I like to do is always start by defining, okay, so let's take a step back and actually explain to people what exactly is a knowledge graph. My way of doing that to people who are perhaps not even to people who perhaps don't even have a background in computer science or data modeling or any of those things is I explain it like this, like, okay, do you know what a spreadsheet is? 99.9 out of people know what a spreadsheet is. So fine. You can think of it as this is a table, basically, right? So a graph is something like a mind map. So you still have data, but instead of having it in a tabular format, it's kind of more free-flowing, and you have connections between the data, and that's a graph. That's a graph in terms of a data model, because, again, people, when talking about graphs, they tend to think about things like visualizations and bars and that kind of stuff. So that's a first useful distinction. But then actually it gets a bit more nuanced, because a graph is not necessarily a knowledge graph. And that's so, to me, the defining, let's say, feature, the defining characteristic of a knowledge graph is the knowledge part, because there's many graphs out there, but it's the knowledge that's attached to a graph that makes it special. Do you agree with that simplistic, maybe, definition?
Yeah, I think it's a good one. I think the other thing that can be helpful to people to understand is when you think of like some well-known graphs, like social networks, like an obvious graph. So like people think about like their Facebook network of their friends, friends of those friends. So I think that often lets people gives people a better understanding. But yeah, I'm interested in what you're saying there about the definition between a graph and a knowledge graph. And yeah, so are you referring there to ontology? Is that
We'll get to that part as well. I mean, if we can agree on the fact that, well, there's different types of graphs. There's graphs that will connect different nodes, and there's graphs that have some kind of knowledge, quote, knowledge attached to them. Then we get to the part like, okay, how do you define this knowledge? Then we start talking about semantics, I guess, and so then kind of eventually and unavoidably, I would say, we get to the part about ontologies. But
yeah, okay. Well, so with graphs, just sticking with the graph part, I guess the key thing that you're doing with the graph above anything else. And at that point, it's like quite interesting to take it back down to the level of maths, I think. So yeah, you could have your data in a set. So you've kind of got set theory, which, that you could kind of see in a way that that's what we're doing with those Excel tables is, we're treating things as sets because the set is like the table basically. And then in a relational databases, you're putting kind of connections between them, but the connections, they're not really first class citizens. And what kind of like the raw bare metal mathematics is with the difference between graph theory and set theory is that we're taking the relationships and we're making them first class citizens. So now you're able to view your data as a network. Viewing your data as a network it's a fundamentally different way of looking at things. And I think it's a powerful way of looking at things because in reality, no piece of information actually exists in isolation. In fact, the context is what gives meaning to pretty much everything. So to that extent, I think all graphs have the inherent potential to bring more knowledge and meaning because they've already taken the first step of acknowledging the interconnectivity of information and the contextual nature of information. So you're already on the kind of first step to the path from turning just plain data into knowledge. But it'd be I'd be keen to. I think it would be fun to dig into like exactly what you mean by knowledge there. That could be like an interesting conversation to have.
Yeah. Okay. So now we're getting to the interesting part. So how do you define knowledge? I mean, in my mind, yes, you're right. If you model your domain, your problem, whatever that is, as a graph, then yes, you're already taking a first step towards enabling discovery, enabling things like pathfinding, graph algorithms. There's a whole range of problems that you can solve by modeling your domain as a graph. So yes, you could argue that, well, you're sort of enabling knowledge discovery, but usually, well, historically, let's say, when people in our community talk about knowledge graphs, they tend to mean something rather more constrained and specific. They tend to talk about the semantics that may be attached to your graph structure. So you can define in specific ways what you are talking about when you have a concept such as a person or a dog or a piece of furniture, and you can also define in specific ways what you are talking about when you attach relations between those concepts, like a person can be the owner of a dog, for example. That already has some kind of meaning. You can add some kind of constraint to that relationship. It can only apply to this concept and that concept. You cannot just, it's not like just a free floating thing that can be attached to anything else, as opposed to a graph that you talked about, social network graphs, for example. Yes, you can discover many things by modeling your social network as a graph. Things like who's an influencer or who knows whom, or how many nodes you need to traverse to connect this person to that person. But they don't necessarily have very good definitions about the people that are modeled in the network themselves, like their professions or how exactly they're related. You can find like, okay, this person knows this person and that person knows that person, but how exactly are they related? They could be relatives, they could be friends, they could be colleagues. If you start specifying things in those ways, I think this is where you get into the knowledge territory.
Yeah. Yeah. So, I mean, again, if we sort of like drop down to bare metal levels for a second, then like people talk about the difference between heterogeneous graphs and like just a normal straight graph. And what do they mean when they're talking about that? Well, I could have a graph where I have these nodes and I connect them with edges, and the edges are all of the same type, basically. So then you exactly as you're saying, you can go and do those kind of pathfinding algorithms that go between it. So I think, but then it could be I could have then the next level up from that's like a bipartite graph. So it could have like two different types of nodes, two different types of thing that are in the graph, like, I don't know, like people and the products that they bought. And so I think the base level definition of a knowledge graph is when you go up to a fully heterogeneous graph. So what that would mean is I can have all sorts of different nodes going on in that graph, and they can have all sorts of different edge types that are connecting them together. So, you know, I could have people and products, and people buy products, and products are shipped to people, and, you know, they are stored in a warehouse. And so as we start attaching as we start attaching, you know, semantics labels to the edges within a graph, and we start saying that the nodes within the graph have got like different types to them, then I think that's our kind of entry level to say that we're talking about a knowledge graph here. So and because the nature of the algorithms that you can run over that, including like the machine learning algorithms that you can run over, it become much more complicated at that point. You know, there's stuff that you can do with quite simply at bare level mathematics with a graph where all the nodes are just the same thing and they've got all the same kind of connections together between them. Once you start kind of saying, well, actually, no, some of these nodes are different things, and the edges between them, they're special different types of edges that mean something, then the complexity goes up, and the algorithms that you're running, so you would have certain algorithms which will run on that very basic one that are not going to be able to run on this more complicated situation. So I think that we could call that kind of entry level to what a knowledge graph is. Things begin to get a little fuzzier, I think, after that, and but I don't think anybody would debate that at least is a fair definition of like the difference between a knowledge graph. And to give you a bit of my kind of backstory and history, I guess I started with knowledge graphs about 10 years ago. I'd just seen Tim Berners-Lee's TED talk on linked data. So I don't know if you've seen that, George. I guess you have, right? Yeah, very, very famous one. And I was doing a yet another ETL project for a large investment bank, kind of bringing data into a data warehouse and doing all the kind of data pipelines. And I just kind of thought there must be a better way. And then I just kind of wondered, well, could like the stuff that Tim Berners-Lee, I mean, at first I kind of thought, you know, what does the guy want? He's already invented the web, and now he's after like a second bite coming and talking to linked data, you know. But then I thought I'll kind of give it a try, and just did like an under the desk little project to start looking at whether I could kind of connect some of the trades together in order to feed into this data warehouse, kind of like a pre-layer, I guess, to the data warehouse. It was passing these semi-structured trade files. I sort of expected it to fail, but it didn't. And then slowly I became more and more obsessed with it, and I'm spending less and less time on my day job and more time like on this little sort of secret side project underneath my desk. My wife's saying to me, you know, Tony, you've really got to stop doing this. You're going to get yourself fired. But so, you know, the kind of bug had me, and I anyway, kind of a long story short there, after sort of several twists and turns, I ended up kind of showing it to the boss there, and they gave me the opportunity to then go and try this stuff out for real. I ended up linking the whole of the FX entire trade population, connecting it into like client data, and we were doing like stuff for finance and closing off regulatory issues with that, and then went and worked on the trading floor with the traders, building knowledge graphs, which was super exciting because we were doing like knowledge graphs that were driving P&L and risk systems. So it's like kind of, if the system makes a mistake, you're in the middle of the night, then you've got people on the phone because it's absolutely crucial, you know, get a decimal position wrong, or, you know, have something, one of those kind of links going in your graph wrong that it's pulling off of this, and it had very big economic impacts if you made like one small mistake, because there's such vast sums of money kind of coming through this particular trading desk. So that was super exciting, and by this point I'm completely now obsessed, and basically it's like I don't care about anything else apart from knowledge graphs now. That kind of phase that people go through where suddenly you see graphs everywhere and everything's a graph now for you. So I kind of had completely crossed through that, and then I started thinking about it in terms of, well, all right, it's working here within this situation, but really what would be like totally cool is if everything was connected together, like all of the information within this large investment bank. Why couldn't it all be connected together? And then I started thinking about, well, it's kind of like a distribution problem. So putting it all into one big graph database is not, you're never going to be able to do it that way. So I sort of became interested at that point in this kind of like idea of taking the actual kind of linked data principles and applying them within the context of one organization. And I was kind of hoping at that point this sort of a bottom-up movement would work there. And to a certain extent it did, but it didn't kind of get to the point where like the whole organization was willing to really buy in whole scale, which by now I was sufficiently obsessed that that's what I wanted. So I moved to a different organization, and there like was architected their sort of another tier one investment bank, and architected their knowledge graph from the top down, so that working with a team of other people there, great ontologists and people who knew about linked data, was all kind of gathered together, and we built a successful project going from the top down there, and kind of out of that sort of really establish some of these kind of architectural patterns that allow you to do the distributed piece. And I guess I should say that just to establish the kind of data layer part of it takes quite a long time. And I'd sort of, before where I was at the first bank, I had done it using these things called GNNs, which I know you'll be familiar with, but for anybody listening, they're like graph-based neural networks, so they're sort of graph-specific ones. And I'd just kind of come to the point in the second bank that I'm at where I'm right, okay, I'm going to start putting in the kind of AI layer now. And at that point, it was like very early in the large language models coming out, like the initial versions of sort of the GPTs were starting to come out. So I thought, there seems to be like some buzz within the community around this. I'm just going to kick the tires on what happens when, trying to use that model in with the, to do the graph stuff as opposed to doing like it all with GNNs. And it was clear like straight away that this was pretty exciting how these two technologies were working together. So then basically I just kind of dropped everything else and just focused in on that particular thing of like, how do you use the large language models with the graphs, and like how is that actually going to kind of work out? And then the most recent evolution, I should say through this time, I was kind of, because I was sort of passionate stroke obsessed with this idea, I've been sharing stuff on LinkedIn, and had people were like finding my posts interesting on LinkedIn. I've become known as the knowledge graph guy there. And so the kind of latest evolution of what I've done is set up a consultancy called the Knowledge Graph Guys, which is an attempt to kind of bring together like seasoned people like yourself that really know about knowledge graphs, and we can kind of come together and enable as many institutions to embrace these patterns, to be able to use generative AI in a safe way, and to be able to connect their data together. So the mission is on to kind of try to disseminate this technology as widely as possible in as short as possible time now. Yeah, I don't know, what's your view there?
I'm thinking, well, in one of the things you mentioned in your one of the things you mentioned in your introduction was Tim Berners-Lee, and his talk on linked data and the whole concept of linked data. And I think it's an interesting starting point. And I have to confess, it was also a kind of aha moment for me as well. Even though I got into the whole knowledge graph and scene, let's say, a bit earlier than that, even though it wasn't called by that name at that time. Doesn't really matter. It has kind of changed lots of different names through times, actually. linked data was one of those names, and hence, by the way, the name of my own brand there, linked data orchestration.
Yeah, we're on the third iteration now, aren't we? Like semantic web, linked data, now knowledge graph. Yeah.
Exactly, and probably somewhere along the way that's going to be something else as well. But when what it comes down is basically the same kind of ideas, the same kind of principles. So I would say, like, yes, I think what you described is a good starting point. This is where you get into the knowledge graph territory. But how do you connect that with the linked data principles, which are actually very specific?
Yeah. So, like linked data in particular, because I mean, as it's kind of gone through those definitions, so it's maybe worth just doing a little bit of history
Yes.
lesson
Yeah.
there. So if we go back to like the semantic web as that was originally, as this stuff was originally conceived, and there, that was something which came out of the AI community and was, what people would now call rather disparagingly good old fashioned AI, like knowledge systems. And we had things like inference engines, and it was about kind of gathering facts and then inferencing what the class is and having first order predicate logic, like symbolic deductive logic, which a computer could, good old fashioned Turing machine style computer uh, could go and run and do computations and come out with answers on. So that was kind of like the first incarnation. But it was called semantic web because it was also like tied up with the web movement. Um, and maybe we can kind of come back to some of that because it kind of comes into the ontology piece, which is interesting.
Hmm.
But like just to the specifics of the linked data, because for me, well, actually, what the linked data was about was Tim Berners-Lee coming back in and just like saying, okay, look, all of the other stuff that's fine. We were in the middle of the AI winter at this point, so like people were kind of like dismissing it because AI was kind of out of fashion. Been this kind of big failure. These neural networks that everyone's banging on about, like they completely don't work, and AI is just a complete damn squib. So in that context, what Tim Berners-Lee did with linked data, in my opinion, was do the decentralization and distribution piece. So he was like, let's refocus back on some of the principles that drive the web, which is essentially that it should be like a decentralized process. We should be using the same mechanism of the web with HTTP and URLs. So now what we're kind of saying is, okay, well, each of these nodes in the graph, what we're going to do is we're going to connect them together by just using URLs. So like if each node now is a URL, like a web page on the web, then I can now put a hyperlink between these two edges of the graph, and I can go and navigate off to that other piece of data, which means that now I can like store these I don't have to store these graphs all in one big database. I can now sort of distribute the process out, which is obviously something I'm very interested in because that was part of my thing of like, okay, well, like, how are you going to like link a whole organization together? Clearly, this thing's got to be decentralized and distributed. So that's really what the linked data thing did. But then I guess it's kind of interesting to say, well, how is a link in linked data different to just a straight up hyperlink on a web page? So, well, the first difference is obviously that when you're going to that link, you're getting data back. You're not getting like an HTML, like a way of doing a visualization, but it's almost like, oh, I go to this end of this hyperlink, and I get back um, the web equivalent of an Excel spreadsheet kind of comes back. I've got structured data that's coming back there. So I guess that's one difference. But the other big difference is hyperlinks. They're all the same. They don't mean anything. Whereas when I've got a link that again, it comes back to the same thing, that I've got a link, and this link is the person, to the order that this person has made. Then I can do the same thing with, I can follow the link for order itself, and then I'm taken to a definition of the semantics, what an order means. And those semantics can be quite nuanced. So what an order means in one organization is not necessarily what an order means in another organization. So um, what I am able to do now, and this is kind of, and I guess we come to this later on, it's like why it's so important now with what's going on with the now that AI is thoroughly not in winter, being able to kind of get that clear semantic definition of what these edges mean is turns out to be a really important thing.
Yeah, yeah, indeed. And another really important thing is the fact that these HTTP identifiers that you talked about are unique.
Yeah,
So it's not just having a graph that's sitting somewhere in isolation, but giving things in your graph, whether they're nodes or edges, giving them unique identifiers means that you can have this distribution that you talked about. So you can have um, a piece of data somewhere in a database and just giving it this unique identifier. You can aggregate with another piece of data sitting in some other database somewhere in a totally different organization even, and you can have a sort of virtualized view over this entire network.
yeah. So globally, yeah, you're creating something globally unique because that's exactly what the DNS system is doing for you, and that obviously is a battle-hardened technology, and more than that, it's a technology and approach that has been proven to be successful. Like the web is the greatest effort that humanity has done, or at least maybe maybe now the large language models, which have basically taken that web and compressed it down, are the next evolution. Maybe they're doing something even more now with that. But the as far as like humanity's collective effort to bring its knowledge and information together, the web is a magnificent effort in that regard. Whatever your feelings about whether it's gone right or wrong, and certain of the initial dreams of it may have sort of gone a little bit awry. I think even Tim Berners-Lee himself wouldn't. Well, I know that he wouldn't disagree with that statement. But regardless of that, in terms of like a proven mechanism for lots of different people, a whole world of people being able to connect their information and knowledge together, it's HTTP works. Enough said. It's just a proven battle hardened technology. So we're just taking that exact same proven battle hardened technology and then applying it now to the underlying data concepts underneath. It's like a no brainer. And I probably shouldn't say this, but I actually sometimes get a little bit annoyed with people reinventing the wheel with some, you see some new flashy term that comes up and is like hyping up, and it's like, well, we really don't need to reinvent the wheel here. We have a really good technology that is proven for solving this distributed data integration problem. You're going to struggle to come up with anything better than this, that has got as much, all of the software that's been written around it, and the security protocols that are over it, the caching optimization, the fact that there's libraries kind of in every language that you could do. There's bare metal stuff that's optimized for it. It's why go off and try and approach the problem from a different angle? Would be my argument.
That's a very good question, but pragmatically, these approaches do exist out there, and so I guess the question then becomes, all right, so these different technologies are out there, and people are using them. So does it really matter? I mean, yes, we've just talked about how great it is that this kind of linked data approach uses these standardized technologies, and the fact that by doing that, you can have these virtualized graphs, and that's really a great approach to do data integration and to solve your data problems. That said, however, if you're not interested in standardization and if you're not interested in having this sort of distributed approach, is it still okay to use some other kind of mm, graph, let's say, approach? Is that a knowledge graph? Does it matter in the end?
Um, I mean, no. My initial answer is no, and I think it's very important to be pragmatic and not dogmatic, and to a certain extent within our community, within the graph community, like they have, they've got like a history of people kind of being rather dogmatic, and I think that's not very helpful. I think if you boil it down, there are two things that are important. I think using your eyes as identifiers is important, and I think having a shared vocabulary and an agreed schema. Those are the two important things. And beyond that, really, the rest of it um, doesn't matter so much. But I think if you're a really small organization, actually just a plain old data warehouse might well do your job for everything that you need. But as soon as you kind of like step up to an organization that's got multiple databases going on, my the hypothesis that I'm running is the siloed approach to, I'm just going to have a bunch of separate databases, each one looking after a particular one of this business, and then I'm going to maybe link a little bit of the information together in order to do some finance reporting and send some information up to the chief executive. That's not going to cut it, in my opinion, in the age of AI. So there's a kind of fundamental massive event on the horizon, which is maybe sort of overhyped on the short term, but is like massively underhyped on the long term. Like people, in my opinion, most people have got no idea what is about to hit them. It might not be coming quite as soon as some of the tech bros would lead us to believe, but actually some of my timelines are shortening now with the kind of the speed which things are accelerating here. So we're about to live in, at least in the next 10-year time frame, in a fundamentally different world, and it could be shorter than that. And in that world, I believe that an organization can no longer afford to have its data in this kind of loosely connected, siloed, disorganized state, because ultimately the value that is the currency, the kind of value of what's going to be going on, the when kind of like vast intelligence is available on tap, it's actually going to come back a lot to what the unique semantics of that business are and the unique data that business is holding. And to get your head around what that really is, it's very, very important to connect it and to do the hard work of like working out, like, I guess we sort of like touch slightly on, oh, we're going to give some meaning to these edges. We're going to have different things in the nodes, and we sort of talked about the semantic web and like some of that stuff that was in there. We mentioned the O word of ontology, but to kind of bring that out and make that when we talk about the importance of having shared schema, but to kind of bring that out and make that all a bit more kind of concrete for people. This is data modeling. This is metadata. This is the kind of abstract concepts, if you like. It's the schema, but schema really does not necessarily do what an ontology is justice, because we've got complicated ways of like modeling inheritance hierarchies, of making properties define classes, or go back the other way back down, and what that does, especially with this kind of graph structure, which, as you said yourself, is kind of like a mind map. So the name of the game is to get as close to the semantics of the business as you possibly can, but within this kind of formal conceptual model. So you're kind of trying to take the words that the business people are using within a given organization, and you're trying to turn those into these formal concepts to kind of like actually get really specific about what they are, and then to connect those concepts together in the way that the concepts interrelate to each other with these kind of like specific type of edges. It's not an easy process to do, and actually generative models can somewhat take out some of the dog work in that. Now it's becoming easier to do that.
Right. So yeah, I think we are kind of gradually approaching towards the O word, the ontology word. And I know that one example that you like to use to sort of onboard people to the idea of data modeling and ontologies and all of that jazz is you refer to schema.org and how schema.org has been doing that for the web that we just talked about. Would you like to just give us the brief version of that and how that all ties back to what you have been saying about the need to integrate and define data on the organizational level and how that's going to serve the goal of having your data inform your AI models.
Mm-hmm. Yeah, no, it's a great point. So yeah, schema.org is something that's out there on the web, and it's what the kind of like web companies have been using to build their own knowledge graph. So you can just go to it like schema.org, tap it into your browser, and you'll see what it has got is the definitions for various different concepts that we talk about on the web. So for instance, there'll be the context. Somebody can always say of a dentist. There'll be like a dentist will be identified there, and the dentist is a type of a service provider, which is a type of a local shop. With whatever the kind of inheritance hierarchy that they've got going on there. And because of that, it will have like opening hours and the services that it offers. So they've basically gone to the effort of like defining the semantics around what it is that a dentist is and the sort of properties that you would expect to get back from that. And then if I am a dentist and I put up my website, then what I can do is in my website, I can include this little island of JSON LD, which is just like JSON, but like it's got a couple of special attributes in it. JSON, for anybody non-technical, is just a way of representing data. So it's a text way of representing data that's incredibly common and ubiquitous amongst developers. And you can take that normal JSON and then you can put this special @context tag, and the @context tag is pointing back to schema.org. So now I can have my little bit of JSON data, and it's got the @context tag pointing back to where the ontology or the schema is lying, which in this case is schema.org. And then it's got a type, and it's saying, well, this is a type of dentist. And then I've got various properties there. So then what the web crawlers are able to do is when they hit that web page, and I'm going to index this web page now on my Google search index, and I see this island of JSON LD there, and I'm like, all right, okay, this is a dentist. I know exactly what that is. And this is structured data that I can then sort of take and suck in. And that's kind of like what's driving those info boxes on the side of Google search. And most people don't know this, but actually almost half of the web has got these islands of JSON LD in it. So this is not like a unused technology or something that's difficult for people to do. Half of the pages on the web. So this is no one knows it. No one really kind of talks about it, but it's a very widely used technology. So, and what it is a shared schema. So there's something quite powerful about that. There's something quite powerful about that concept because we've got the URLs, and that means that we can go and resolve them over the web to someone else. So, schema.org is hosting their definition of what these concepts are. I can follow the URL of schema.org. I can follow the URL of what dentist is, and I can go back and I can get this definition there of what dentist is. And what that means is that the process of the data integration, the cost of it has been taken from the person who's aggregating the data, and it's passed the cost on to the person who is providing the data. So Google and Microsoft don't pay the cost of doing the data integration. The dentist pays the cost of doing data integration because he wants to come up higher in their search indexes. And that is the trick, in my opinion, that pretty much all organizations need to perform. So they need to have their own internal version of schema.org that's got their own specific semantics within it that reflect the semantics of their particular niche and their particular business. And then they need to try to get as much of their organization as possible to buy into producing and publishing their data in conformance with those shared semantics. And because you've got things like inheritance that, I can have a slightly different version of what my dentist thing is, but I'm going to inherit the characteristics of this shared definition. So that's people don't realize it, but that is like a massive magic trick. And it's something that has not been performed yet, really, because, even if we're talking about like creating a data mesh and creating data products, that's great, that's decentralized. But what you're really wanting to do is you're wanting to decentralize the effort of doing the data integration. That's the nub of where the hard part of the problem is here, is kind of linking stuff together and conforming to some shared terms. And just briefly, why is that important then with AI? And we can kind of get onto it a little bit more. But you're creating your training sets for AI there. You're defining that nature of your business in a formal way. You're then connecting instances of data to those formal semantic concepts. So you're doing the job that needs to be done in order to get yourself through. Once this massive event comes in of whatever it looks like with this kind of general AI event comes through, the the organizations that are going through to the other side of that, in my opinion, are the ones which have done this task, and we've got this window in order to do it.
Mhm. Yeah, actually, I think part of the reason why some organizations, at least, are lured by the promise of, well, AI is going to solve our problems is precisely because they believe that, well, what all we need to do is just feed our data to the AI, the magic AI model, and presto, it's going to just make sense of everything. And I think what they don't realize is that it's just going to create a mess if they don't actually pay the upfront work that needs to be done to define what exactly is in that data that they're going to feed to the AI model. Because I think a very typical example is things like sales or products or customers. If you have a dozen systems or even a couple of systems in your organization, chances are these things are going to be repeated, are going to be reused across different systems and not exactly in the same way. So system A will define customer in a certain way, and system B will define again customer in a slightly different way. So if you feed data from both of those sources to your AI model, what's going to come out? Something kind of jumbled and inconsistent, right?
Yeah, I think that's absolutely it. So there's a few things to say to it. So, like, first of all organizations are going to have to accept the reality that they're moving to a more probabilistic world. So, like, everyone has got to start using AI, or you're probably going to go out of business, which means that we're moving to this new world where, like, stuff will be probabilistic, and AI will be embedded in, like, a lot of this kind of decision making. So I think that that's just a kind of, you might not like it, or you might have whatever opinion, but it doesn't care. It's like kind of some force of nature or whatever that's happening, and it's happening. So you might as well just kind of get used to it. But so then the question really becomes, well, how do you do that in a kind of safe way? And in my opinion, that comes through, like, external verification. So um, it's quite interesting if you take, like, you've probably seen, like, all of the hype over DeepSeek, and, like, the big impact that had on the stock market with them coming in and recently and doing their version of generative model. And so, like everyone else, I was kind of obsessing with it and going back and kind of looking at it and try and work out, what it is that they did. And they did some quite really interesting changes algorithmically. But the bit that really struck out to me is that, kind of sitting at the heart of what they did, how they got their model to be good, is they kind of took all of the web data, like everybody is doing, but then they pulled out, like, just the ones that were related to mathematics and the ones that were related to coding. And then with that, what you can do is you can create an external verifier. So you can basically look at the bit of the maths, and then you can look at the answer at the end, and then you can check whether the answer is actually correct, and likewise with the code. And then you can feed that to the large language model and ask the large language model to do that, and then check it against the external formal verifier. And what that is basically doing is kind of putting quality control upon the probabilistic model. So you're going out of, this is where I kind of like talk about the continuous world and the discrete world. So you kind of, in the continuous world, everything's probabilistic, everything's fuzzy, and that's where these kind of generative models are. Like, one thing blends into another, and you get hallucination. But you flip hallucination on the other side, and there's something a bit like creativity there. It's, able to explore off to these kind of different places. Talking back to the old world of the semantic web, we had this thing called the Psych project, which, it failed because we were trying to do complete general knowledge in a formal way, and it was just like it was an absolutely horrendous task. This succeeds at that. This succeeds at what that was unable to do because of its probabilistic nature. But it has got these dangers. You want to go use one of these systems in to do Something within the financial domain or in the medical domain, absolutely, in the legal domain, absolutely no way you're going to let loose something like that that's going to do those things. So then the question comes, okay, well, you've got these kind of like for maths and coding, it's quite obvious what your formal verifier is, because with maths you've got the answer there, or even you could go out to some kind of system like Lean or something like that, where they've actually got the acronyms in there. I don't think that the DeepSeek team did that, but others are. With code, you can see if it compiles. You can maybe even write, get the LM to write a couple of unit tests and see whether the answers are coming out right. You're using the code compiler as the formal logical system there. So you have this really interesting thing then. Well, what's going to be, how is a given organization going to do that? Well, at the base level, again, let's go back to bare metal. So we go back to bare metal first principles. In our probabilistic fuzzy world, if we are sort of modeling mathematically probabilities in this kind of across multiple different factors that we would call like dimensions, then we create this vector. Okay, and people talk about it like vector embedding. So I've got my vector database. When people are talking about that stuff, that's what they're talking about. Big long list of floating point numbers. That's essentially what you get out of behind a large neural network is, when they talk about the weights of the model, that's what it is. Like these big long list of floating point numbers. In maths, when you're wanting to, and that's in the continuous world. So you can almost see that like a kind of like, let's now not talk about the trillion parameter models that we've got with these giant things. Let's simplify things for ourselves, and let's imagine that we're just now down into 2 dimensions. Well, it's quite simple now, and we can think of it like coordinates on a map. And I've got my latitude and my longitude, and that's going to take me, it depends on the scale of the map, to be honest with you, like where it's going to take me, but it's going to take me to some region within that space. And that's essentially like what we're getting with the kind of vector embeddings. And that's how, and the structure that we would represent that with would be a vector, or sometimes tensors and stuff like that. If you're going to do discrete mathematics, on the other hand, like if you went to a mathematician and said, how are you going to do like discrete mathematics? Well, like 99 times out of 100, you'd use a graph structure to do that. The graph is the structure that you would turn to in order to kind of do things like discretely. And what do we mean by discretely? Well, you're basically kind of putting boundaries around stuff. It's no longer probabilistic and fuzzy. It's like, okay, there's this thing, it's connected to this other thing, it's connected to this other thing. I can compute over that. I can validate over that. I can do formal verification over that. So now let's zoom right back up from the bare metal to the other thing. We've got our ontology, we've got our graph, we've got our large language model, we've got the fuzzy, probabilistic, scary, but kind of almost human, creative, hallucinating thing over here. And then we've got our kind of like discrete, computable, validatable part here, and stick the two together. And this is exactly why knowledge graphs are sort of zooming up the hype scale at the moment, with Gartner identifying them as being, the enabling technology of Gen AI.
Well, playing the devil's advocate here, someone might tell you, great, that all sounds great in theory, but how does that actually work out in practice? Right, I'm sold to the idea. I'm going to start creating my own organizational ontology, and then what? What can I actually do with that? How can I use it to interact with an AI model in a meaningful way? And I'm going to sit here a little bit by sort of previewing your answer. I've seen you advocate a concept called the working memory graph, which I guess is a way of conceptualizing this interaction. So I'm going to let you talk through it, and then I have a couple of specific questions on how that plays in practice at this point in time.
Yeah. Okay. So, all right. The idea of the working memory graph is that you basically let's assume that the ontology has been created and the knowledge graph has been created. which are two big assumptions, and it might well be worth looping back to the fact that in order to create those, we use generative AI not to create them on their own, but with humans in the loop, you use it as a tool to lower the effort of doing that. But okay, zooming past that and assuming that that bit is in place now. So I've got a good ontology, which is like a formal conceptualization of my domain with the key concepts within it, and I've got a knowledge graph, which is connecting to those concepts and giving me kind of facts about it. So now, like, the user could ask a question. You could have like just like you've got ChatGTP. You're working within a given organization, and you bring up your semantic agent that is your AI agent with your private version of the large language model, generative AI model coming up there, and you say to it, read through this document and give me the probability that the mortgages in this, the NBS mentioned in it, are likely to default or something like that. Like some, or depending upon your domain, whatever that is, some highly technical thing that is relevant to what you're doing, that a general large language model would not be able to answer, because it has been trained on all of the general information in the world, and it's not got the specific information about your organization, and it hasn't got the specific know-how and knowledge of your experts. So what the large language model can do is it can look at that query and understand that query, and it can do this thing called RAG, and then this thing that we call graph RAG, which takes various different flavors. But in the conception I'm going to give you with the working memory graph, the first thing it's going to do is actually just go off to the ontology, and it's going to try and identify the concepts that are being mentioned in here. I see you're talking about an NBS. I know what an NBS is. It's mortgage-backed security. It's like a type, or it's a type of bond. I know about the semantic. Yeah, I know about them. And then you're asking for like default. Okay, yeah, this is our definition of what default is, blah, 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 blah. Are there any facts around the graph that are maybe relevant to doing that? Can I, when I'm looking at this document, what properties am I expecting to pull out that I know MPSs generally have and that are maybe relevant to do this thing? Now I end up with the situation with the working memory graph. I've got the large language model at one side, and now I've got like a subgraph of discrete facts on the other side. And now I can basically kind of loop between these two structures. So like going from the formal verifiable version down to the using the large language model. So the large language model is going to kind of do exploration and creativity. The graph is going to give you like discrete formalization, and then kind of giving, yes, no answers maybe, but you're kind of slightly on the wrong track here. So, imagine, take a different formal system, take a mathematical verifier. So imagine now over here, we've got a mathematical verifier. So like alpha geometry. In alpha geometry, basically you had like a custom trained large language model, which is kind of coming up with ideas of, I want to solve this geometry problem, right? Okay, my idea is solving the geometry of this problem, right? I'm now going to send it into the formal verifier, which is going to compute whether that answer is correct or not, and then it's going to reply back to the large language model saying, no, you're off by this because such and such don't work out. And basically what we're talking about here with the working memory graph is a domain-specific version of that. Harder to do, much, much harder to do. But basically, I think the only game in town that I mean, I'm biased, obviously, but the only game in town I see for all organizations that want to survive the event is to kind of get really crisp on what these semantics are, connect your data, be able to do that kind of formal verification.
All right. So, a couple of questions
Clear,
here.
or it's not so clear?
Mhm. So, yeah, a couple of questions here. So, what you're talking about is a kind of two-way relationship between building your ontology and knowledge graph and using your large language model. So, one of the ways that you see this interaction happening is using an AI model to help you create an ontology and a knowledge graph. And so, my question there is, what has your experience been in the current state of affairs there? And to kind of preamble this, my own experience has been kind of so and so, let's say. I mean, yes, you can use. I've tried a couple of different options, not all of them, admittedly. So I may be missing something. I have to say this up front. But in my experience, the kind of tools that I've used have been able to get something out of, you feed them a lot of textual documents basically, and you expect them to give you something that resembles a kind of coherent data model for the domain that your documents are describing. My experience has been kind of hit and miss. So yes, they are able to extract some kind of concepts, some kind of relationships, but what you get out of the box is really not usable. It's not really production level. You have to put in additional effort to be able to come up with something that's usable. So I kind of question whether it's actually worth doing that in the first place. Maybe you're better off just starting doing everything manually. I don't know what your experience has been.
Yeah, I mean, there are some tricks, which would be too detailed to go into now, but my experience has been very positive, actually, and only getting more so as the models, particularly with the reasoning models that are kicking in now. Yeah, it's kind of just getting better and better. So no, I think it's good. Is it 100% of the way there? No, it's not. And actually, that's a good thing, because if you're simply able to take a AI model and show it one of the documents and say, tell me everything that's going on in this document to the level of expertise that the people inside a given niche of a business are able to do, that means the value of your business has just dropped down to the price of a call to one of these models. So like 0.01 dollars or something like, or even less now that we've got the DeepSeek, etc. out there. So this is a good thing. So that what the large language model is able to do, in my opinion, is take between somewhere up to 80 to 90% of the dog work effort out of doing this thing, and then the rest does come over down to the experts. But basically, what you're able to do is, like, within, like, if you kind of like flip over to the machine learning side, let me talk about this thing of like the latent space. So this is the kind of part within the neural networks. We've got the input layer, you've got the kind of output layer that comes off the other side, and in between that you've got the latent space, which is this kind of like black box of whether the machine learning model is learning what it's kind of learning, and has got these latent representations, which um, you know, there's a lot of kind of debate that people go, do these things have like world models, and do they have like conceptual understanding? But to my mind, they do create these abstract concepts within there. They have to do that because they're basically compressing large amounts of information, the whole of the information on the web and more. They're compressing that down to like quite a small number of floating point numbers. In order to do that compression, they have to compress some of the semantic information. So they have to compress information about some of the concepts in. But they do it in a way that's completely interpretable by humans, and we would never sort of be able to begin to understand how that's done. I mean, just as you wouldn't, you couldn't look into someone's brain and look at their neurons to understand what they're doing. So by using the large language model to show an instance of a data and then get it to help you to get it do like a first stab at what the conceptual ontology is doing, is kind of a bit like looking into the latent space of the large language model. You're getting to kind of pull out some of those concepts and put them into a discrete form and see the network of how that they link together with each other. And once you've got that, that's when the domain experts can come in. And this is where the business is adding its own value. So this is, in some ways, the really important piece, because the bit where the large language model can do on its own is kind of like the gestalt knowledge that everybody has already got. So that's the bit that's worth $0.001. Now we come to the bit that's actually going to be worth something post the AI full-on event, which is not really coming in like that, but it's it's going to be more of a gradual process. But post that coming, the bit that's actually the large language model can't do and isn't part of the general knowledge of the world is the part that's actually got the value. And that's where your people can come in and they can make the changes in there and say, no, actually, it's much more nuanced than this. And or it's got this conception of it's wrong, it's like this. So that's really valuable work that's being done at that point and shouldn't be degraded. But who wants to do the boring bit that everybody else knows? You know, you only want to kind of do the bit where you're the specialist and you're adding some value. And that's how these two things, well, really, it's three things working in conjunction. It's the large language model taking the Gestalt knowledge and doing a load of dog work. It's the formalization of the model in what we've got with the technology of ontologies and knowledge graphs, and then of course it's the humans that are able to kind of work in at this kind of discrete conceptual level and go and make their changes, which are then fed back into the large language model. And now when you say, oh no, here's this more nuanced understanding of what this concept actually is, the next time the large language model reads that document, it's able to refer back to your conceptual models, and now it knows what you would know. You've distilled your knowledge into this very crisp formal format. And then when it comes back out the other end, if it's made a mistake or hallucinated or got something wrong, your model can catch it.
Right. So that's precisely what my next question was going to be about. Like, fine, okay, so let's assume that one way or another you've gotten your ontology, and then you're trying to use it to guide, to steer your language model towards, to provide some context towards getting an answer that's, well, less, that contains less hallucination, let's say. Again, in my experience, and I also have to say that I've seen people use various flavors of, well, templates, or I don't know, instructions or whatever other constructs, let's say, that they refer to by by using the term ontology, which in my opinion is a bit confusing again. But anyhow, that aside, that kind of pet peeve aside, let's assume that, through whatever way you've gotten to the point where you have an ontology, whatever form that ontology may actually assume. What In my experience, it still doesn't entirely rid you of hallucination. So how do you actually, you still have to put in some work to verify that whatever it is that you get back actually holds.
Yeah.
What's your experience been, and how
Yeah.
do you see a way out of it?
The same, and the way out of it. So I call this pattern like the neural symbolic loop. I've got all of these like kind of strange names to these various, like working memory graph and neural symbolic loop, but they're kind of, in a way, the working memory graph is like, okay, this is how I'm going to do the answering of the question. The broader pattern that sits within is this thing I call the neural symbolic loop, which is that you're iterating between continuous and discrete structures until you get something that you're happy with. So we kind of like we've been one way through the loop in order to take the formalized concepts, put them into the context of the large language model, allow the large language model to do its job because you're kind of steering it by those formalized concepts. Then the information comes out of the large language model, and we can convert that information back into a kind of discrete form of a graph. And then once we've got that in a discrete form of a graph, we can actually then, use the ontological model that we've got there, plus the factual data that we've got in the subgraph, to validate that this makes sense. Like I put constraints in on some of these relationships, like I'm trying to think of a good example off the top of my head, but like a dog can't have 6 legs or something like that. It's got a max of all mammals have got, like, well, not all mammals. Yeah, we can say all mammals have 4 legs. Anyway,
Who knows?
yeah, but you've put in whatever constraints are, and then you can do that constraint checking against what's coming out of it. So has it made a completely something that would send it down, and you can then block off paths that basically are obvious hallucinations.
Okay.
And then you can feed back. I'm sorry, large language model. You seem to have said that this dog has got 6 legs. That's not correct. Dogs have got a max of 4 legs. Try again.
Right. Okay, so yeah, verification is still needed, but suggested way out of it is, well, you sort of you translate back to something that is verifiable, and you do the verification part, and if the verification fails, you go again and you try to course correct, basically.
That's right.
Okay, cool. All right, I think we're almost running out of time. If we're kind of slightly over already, so let's wrap up by something that's a bit related to the most hyped topic of the day of these days. So you already kind of talked about it. So DeepSeek and reasoning, or so-called reasoning models. Again, there's a bit of disconnect, let's say, in terminology here, because, well, what people in the knowledge graph community have traditionally been referring to when they use the term reasoning is something that's kind of tractable, deterministic. You already again talked about it in one of your opening remarks, and as opposed to that, what these so-called reasoning models do is something quite different. So I've seen you being in support of the statement that, well, eventually these models will be able to mimic reasoning so well that it's going to be indistinguishable from actual tractable reasoning. And I don't know if we'll ever get to that point, but I think that's an interesting prediction anyhow. And just to kind of again play devil's advocate here. So as you also said at some point, the way that these models are trained are basically by extracting verifiable statements out of otherwise very big and potentially messy training data sets, and focusing on those. However, I've seen research that, and their claim to reasoning fame, so to speak, is the fact that they score very well on benchmarks that were specifically designed to measure reasoning capabilities. However, I've already seen people do research and sort of prove that even on those tests that are included in those benchmarks, if you variate slightly on the very questions that are included in those benchmarks, those models will fail. So I don't know what that tells us exactly.
Yeah, that's a really good one. And this opinion of mine is not at all popular in the rest of my community. It goes down like a lead balloon whenever I say this one to the within the graph community. So I guess, all right, let's let's kind of break it down. Like, so first of all, reasoning, it's a bit of a loaded term, and everyone's talking about it so much that it's one of those ones that's maybe becoming on the edge of like, how useful is it? Because reasoning seems to mean different things to different people. But like, one of the things I quite like is if you sort of look at large language models as doing logical deductive reasoning. So like what we would call formal reasoning with first order predicate logic, that sort of thing, and compare that to like the different, there are actually kind of different ways of reasoning out of a problem. So that type of reasoning really probably is only one type of reasoning, and it's the type that our community is particularly keen on, and it's got a lot of benefits to it. But like, actually, coming back to the Psych project again, and a huge admiration for all the people who worked on the Psych project. I think it was like a brilliant endeavor. But you know, to do some of this stuff, it just makes more sense to do it. Some things, there is no like exact truth to it. It makes sense to be working in this kind of probabilistic sort of space. So having like kind of inductive versus deductive reasoning, having the two working together with each other, I think that's the best way of doing it. And that's certainly where we are right now at the moment. I could, you wouldn't get a stronger advocate for a formal verifier than myself. That's exactly everything that I'm talking about. That organizations need formal verifiers, but Nevertheless, with Rich Sutton's bitter lesson and everything like that, there's the continual surprising effects of things learning stuff for themselves. And actually now with these models, and when you're bringing like RL into it, the reinforcement learning into it, the reinforcement learning does have the capability to go beyond what just the kind of large language models on themselves were able to do. But even though what's surprising with DeepSeek is that many of us kind of suspected there was a bit of an RL going or something like that going on at inference time, but it doesn't even look like it kind of needed that. It just looks like the RL was used to train it so that it would spit out the thought processes that was going on, and by sticking out those thought processes, it's able to get a closer approximation of what reasoning looks like. Now, what it's, I guess, not going to be able to do is like create like a fully symbolic function where, the large language model is probably just never going to be able to create those fully symbolic functions where, like a mathematical function where I'm going to pass a couple of things in. And once I've defined that mathematical function, this thing is always going to precisely come out with the same answer every single time. They are of the continuous nature, and that symbolic nature of doing that is something that they're not going to be able to probably ever do, although they're getting better and better at approximating it. But humans can't do that either. My kind of in-head maths is absolutely terrible. So, we use tools in order to do those things, and they too will be able to use tools. So with a combination of like a bit of tool use, a bit of external verification, maybe on like some kind of like formal structures, then it will be, and even just the kind of models on their own, like the way that they're improving, I think they will, they're already demonstrating that the level to which the mathematics that they're able to do, etc., is, it's shockingly good. And everybody, that people always come up with the examples that kind of crush them down, and these are the kind of edge cases. But look back to some of those ones that were being, take any of the original ones that people were finding at the beginning, which were laughable, and they're all kind of gone now. And I think that process, I would expect to continue over the next period until the point where it's increasingly hard to trip these things up.
Well, let's see how it all unfolds. It's certainly going to be interesting to watch. All right, so thanks. I don't know if you have any kind of closing statement or anything that you'd like people who may be listening to take away from all of this.
Yeah, my big message that I try and hammer down to everybody that is working in organizations at the moment is that it's very easy to get distracted by the tip of this AI iceberg. So the glittering algorithms, the reasoning models, all of this kind of stuff that's doing the clever stuff on the top. Don't get distracted by that. That's off and it's going, and there's nothing anybody can do to stop it. It's like some massive geopolitical economic event that's going, that major powers and huge amounts of money and billions and trillions of dollars and other currencies are going to be pumped into doing. That's off like a rocket, and there's pretty much nothing anybody can do to stop that. That's happening anyway. So you're going to be then in your organization, you're going to be in a situation where you're going to be able to import this general intelligence in. So you've got this period of time now before this stuff it's smart at the moment, but like you were just pointing out, it's not super smart. In my opinion, it's going to get super smart, and in quite a lot of other people's opinions as well. We'll see, but I would hedge on it getting super smart within the next 5 to 10 year framework. It's going to get super smart. I believe some other people it's even down to like 3 years. I think that's over optimistic, but we'll see. Who knows? You've got this short window. So what you need to do is concentrate on the bottom of the, you need to take it to the context of your organization, and you need to concentrate on the bottom of the AI iceberg, which is the data. So you need to take the power that we've got on the models that we have at our hands right now, and you need to focus that back upon the data that you've got in there. You need to clean and consolidate the data up so that it's in a state to be an effective external verifier, and that you're aware of what information is worth 0.000 $1 and what information only you have and is the value add that you're adding. And you need to connect that and you need to consolidate that down, because that's the only that's the only game in town as far as I see at the moment for a huge number of organizations.
Okay, well, that's pretty clear and well, pretty powerful, I would say as well. So, thanks a lot for your time. It's been a super interesting conversation, and I
It's been
hope
great.
people will like it as well.
Yeah, it's cool chatting with you, George.
Thanks for sticking around. For more stories like this, check the link in bio and follow Link Data Orchestration.